today's Saratech enablement session. My name is Andrea Hall, and I am the Customer Relationship Manager here at Saratech, and I'll be your host. Presenting today from Markforged, we have LaShawn Mu, and he is going to be talking to you about 3D printing in general, how to go from CAD to part, and of course, highlighting some of the awesome packages that we have with Markforged. Our sessions run about 30 minutes each, and they are all recorded and posted to our Saratech YouTube channel. Make sure that you check out our past sessions there. We meet here about twice a month, and we just talk about tips and tricks and new and old features that will help you in your everyday tasks. This is an open forum, so if you have any questions or comments during the presentation, please don't hesitate to type them into the questions box over to the right. And I will kindly interrupt LaShawn and just let him know about your questions and comments right there on the spot during the presentation. And with that, I am going to pass it on.
Thank you, Andrea. Hey guys, thank you very much for your time today. My name, as Andrea pointed out, is LaShawn Mu. I'm the application engineer at Markforged. My role as an application engineer is to help customers like yourself identify areas in their business where they can leverage Markforged's technology, whether it be the composite 3D printing or the metal 3D printing. So a little bit about myself. I graduated from Georgia Tech with a master's in mechanical engineering. I started my career off at Schlumberger as a mechanical engineer, working closely with manufacturing as well as new product development. Then I went to Pratt & Whitney, where I also worked very closely with our manufacturing team doing product development, new product development. And from there, I went to Markforged and began my career as an application engineer. So the agenda for today, we're going to discuss why use 3D printing. And we're going to CAD to a 3D printed part in 15 minutes, give a high-level overview of the 3D printing process, how we adapt existing designs for 3D printing, and we'll go over a case study on how we took a part, quickly iterated that part, and then printed it. And as Andrea said, feel free to type in your questions, and Andrea will stop me at any point, and I can answer those questions. So why use 3D printing? You don't have to wait weeks and weeks for results. Right? You're able to rapidly iterate your designs, avoid the lengthy internal PO processes, request for quote processes, and mature your engineering work quicker. Right? This is kind of the typical timeline for machining a tooling or machining a part today. Right? You design your tooling in CAD. You have to create a drawing. There's a backlog period where you get your POs, your request for quotes, and then you have to get signatures, sign-offs for that part to actually even go out. And that's if you shop it out to a third party for machining. Let's say you're saying, hey, I don't have any backlog if I do it internally. I have a machine that can machine that tooling. Well, that machine, that CNC machine, or whether it be a manual machine, that machine can be used for other things other than tooling. It could be working on production parts. It could have a whole queue of projects that it needs to work on, so you still have a backlog, whether it be internal or you're externally having it machined. And after machining, you get the delivery, right? So this is your total machining production time, so that equates to one design iteration. With 3D printing, that becomes a lot simpler. You can go from a CAD to a 3D printed part in your hand, skipping over creating a print or a drawing, skipping over the backlog of submitting an RFQ, getting the signature sign off, submitting a PO, getting that part delivered, or even waiting in line for one of your machines to open up. You drastically shorten your design iteration time. So within the same amount of time that it took you to get Rev A in traditional manufacturing, you're able to go to Rev B, Rev C. So quickly arrive at your final part a lot quicker. And that's not even saying the amount of iterations you can have per print. So within the same amount of time it took you to traditionally machine one rev of a tooling, one iteration of a tooling, you can print 3 different iterations for the same amount of time, maybe 4 different iterations, 5 different iterations. So here's kind of the cost per part when you're looking at machining or casting, the more traditional, conventional manufacturing methods that you see or use today, right? For a single part, your cost is very high for that part. Your economies of scale does not kick in until you go to a production volume where you're producing hundreds, thousands, hundreds of thousands. With 3D printing, you're kind of staying around the same price per part. When you start getting your economies of scale, that's when your traditional manufacturing beats out 3D printing. So there is a break-even point. And where we try to live is this area before the break-even point. At what production volume these one-off parts, one-off fixtures, one-off tooling that you're doing that's costing you a fortune, costing you a lot of lead time. You're just sitting around twiddling your thumbs waiting for parts to come in that could take 4 to 6 weeks that are simple machine parts, but because you're doing it at such low volumes, you have to pay extra to get that part machined on one of their production machines or on one of their machines. You have to wait a very long time unless you pay a premium to shorten that lead time. So how do we get from a CAD to a 3D printed part in 15 minutes, skipping the drawing, skipping the backlog of RFQs, POs, delivery times? This is what the 3D printing workflow typically looks like. You first design your part in CAD. You put that part into our slicing software. And what that slicing software will do is determine the G code or kind of the print, where the print head should go to print that part. And then you print it, and you have a part in your printer today. So for example, this is one of our customers. They're called Dixon Valves. They worked on these gripper jaws that grip the coupling. And they had a set of 3 of these. And these gripper jaws had to be very conformal, had to be strong, had to withstand corrosive environments. So they had a lot of requirements. These were traditionally made in metal, machined in metal. A typical blank of a gripper jaw looks something like this. And I'm going to hop over to my CAD software and I'll show you what we were able to do very quickly in 15 minutes to make a conformal jaw. For instance, this is the blank jaw, gripper jaw that we were looking at. We pull in the coupling. We position that coupling onto where your gripper jaw is. You can see where there's a little bit of an intersection here because we want that conformal geometry of this coupling on our jaw. Taking a Boolean subtract, we're going to remove away that geometry. I'm going to hide the coupling here, and you can kind of see the missing area now where that conformal geometry is now imprinted on the gripper jaw. From there, I'm going to clean up some of the surfaces. All right, I'm going to add key insert channels. What that's going to do is, because that coupling is metal, our base material is called onyx, the black material. It's called onyx, and it's a nylon 6 base material. Over time, as you rub a metal part against a nylon part, you're going to wear away some of the surface here, making your conformal surface out of tolerance. So we created channels here in order to use off-the-shelf key inserts to act as wear surfaces, therefore extending the life of our jaw. So from here, we're going to clean up some of those surfaces, add some fillets, add some chamfers, take away some of the sharp edges, and then simply mirror that part. All right, and now you have a set of jaws that are going to be conformal to holding this coupling. So that's the CAD part. And now we're going to take it into what's called slicing. So into Markforged slicing software. It's called Eiger. I've already imported in here. The import is fairly easy to do. All you have to do is drag and drop, or you can upload from your library. So from here, I'm going to click into my sliced part. So this is that jaw that we just designed here in our CAD software, right? This jaw, designed in CAD, I imported as an STL into our slicing software. That part is now ready to print. At default, we have added the settings to optimize the print for your part. So once you upload your part to Eiger, you save it, it's already pre-sliced. All your settings on the right-hand side that you can change, but you can leave it at default and hit print. The information on how much it's going to cost due to material. This jaw, one jaw, is going to cost $5.96. You're going to take about 5.5 hours to print. From here, you can dive into whether or not you want to add any kind of reinforcement, which I'll go over in a minute in my presentation. And that fiber reinforcement is what makes these parts strong. So that's the part, upload it into Eiger. From there, you just change up your settings if you need to, hit print, and you'll have your part in your hand. So just a little overview of the 3D printing process. Like I said, it goes from designing in your own CAD software to placing it into some slicing software and then hitting print. So what is slicing? Sorry?
I'm sorry, I have a question. We have a question here.
Yes.
So Jim wants to know, do you offer or do you have any training videos or anything that they can follow up with after this presentation?
Yes, we have our blog. I believe it's, if you Google Markforged, our company name, and blog, you should be able to reference our blog, and there are best practices on there. There are videos, there's text, there's links to also our YouTube channel. If you just search YouTube Markforged, you should be able to find a lot of content that we have published on training you how to leverage some of our either post-print, and I'll go into some how you put in threads, into designing for additive manufacturing, designing for our continuous fiber filament. All that's on our blog or on our YouTube channel.
Okay, awesome. And I assume that you're constantly adding new videos and blogs and things like that, right?
Yep, correct. We're ramping up hiring over the next couple of weeks into next year as well, and building out our content team so that we can provide these supporting documents. And we're generating documents that we publish daily, videos that we publish constantly, and we're putting out new video all the time. So definitely keep up with us on social media, and we can also follow up after this with a design for composite design guide, as well as design for metal design guide.
Oh, okay. Maybe we can attach that when we send out the replay of this session.
Yeah, that'd be great.
Okay, great. Thank you.
No problem. And so this is the part that we were just looking at. You can see this CAD has the key inserts, the off-the-shelf key inserts already in there. So we go from CAD to slicing. Now, some of you guys might have a question, what exactly is slicing? So you can imagine at your deli, you have your ham, and there's a slicer. What it's doing, the program is doing, is it's taking your CADed part, and it's doing just that. It's taking it layer by layer and producing a G-code on how to move the print head in order to print that layer. So depending on how you orient your part, how you configure your part, you know, how dense you want the infill, how hollow you want the infill, what kind of fiber you want in your part to reinforce your part, the slicing software is going to divide that part into however many layers and then produce the communication, the G code, to the printer in order to actually print your part. So taking that Dixon Valves gripper jaw, it's taking slices layer by layer and then reproducing it. Very similar to how CNC has CAM software, 3D printing has slicing software. So there are a lot of 3D printing solutions out there. On this page itself, you can see there's almost over 12 different 3D printing technologies, right? Ours fall into FDM, or extrusion-based 3D printing. Imagine a very high precision glue gun that's extruding the onyx material layer by layer to produce your part. So this is what kind of a very high level look at what a rudimentary look at what a 3D printed part would look like. And so this is where Markforged kind of separates itself from all the 12 3D printing technologies out there, and even with extrusion-based 3D printing, where the high precision glue gun, we have what's called continuous filament fabrication. So what that means is you design your part in CAD, you can slice your part, and during the slicing phase, as I was showing you earlier in our slicing software, you can reinforce your part with Kevlar, fiberglass, or carbon fiber. So those three options allow you to reinforce your part, therefore making it as strong as 6061 aluminum and making it capable of replacing tooling, fixtures, jigs on your shop floor. Going from the slicing software sends over the print information to your printer, and it just prints, and you walk away. So once again, we're looking at these Dixon valve gripper jaws. This is kind of what it looks like in a rudimentary sense when we lay in that continuous filament or fiber filament, right? We're taking a cross section of that part. Let's say it's printing up to this point. What it's doing is it's laying in the fiber continuously in a continuous strand around the perimeter of your part. Now, a lot of companies out there are beginning to tell customers that they can print in carbon fiber. What they don't communicate is whether those are short strand fibers or continuous fibers. We are the only company in the world that can print in continuous fiber. That's because we have the patent on that technology. That's the bread and butter. That's where kind of how we were founded, is we wanted to print in carbon fiber, and having just chopped carbon fiber or short strand carbon fiber wasn't going to be strong enough. Our onyx material, so our base polymer material, already contains chopped carbon fiber. That chopped carbon fiber makes our parts already 20 to 30% stronger than ABS, or what I like to call the gold standard of 3D printing materials. It's already stronger than ABS. It's when you add in the continuous fiber, whether it be fiberglass, Kevlar, or carbon fiber, to reinforce your part, that's when you're going to be able to use it for functional prototyping, when you're able to use it for functional tooling, functional jigs and fixtures, CMM fixtures. And this is what it actually looks like in real life. So this is an actual cutaway of a part, one of those Dixon gripper jaws, showing the continuous fiber that's routed on the perimeter of the part. And on the inside, you can see there's that triangular grid pattern. That's our hollow infill. So you will actually have a honeycomb hollow infill through your part, 1 saving on material, 2 saving on print time, and 3 saving on weight. And that was significant for Dixon valves because if you imagine these gripper jaws, 3 of them are picking up something every day, moving it to another spot for machining. And as it goes through these motions, any kind of reduction in weight increases efficiency, increases life of that robotic arm. This is the part sitting in our Mark II 3D printer. So now we're going to talk about, that was all composite 3D printing. So this printer, Mark II here, is our composite 3D printer. That's the one that does the onyx-based polymer, as well as your continuous fibers. Currently what you see in here is a Kevlar loaded, it's yellow. You have fiberglass that's white, and your carbon fiber that's black. Our metal printing solution uses what's called atomic diffusion additive manufacturing. So opposed to what DMLS or your traditional metal printing where it has metal powder, our process actually does not have free-flowing powder. All that powder is contained in a binder material when it's printed. It stays in the binder after it washes, where it gets debound a little bit. So there's wax and a polymer that's actually holding the metal powder. And that metal powder doesn't get sintered until it goes into the sintering oven. So this process, the atom process, is kind of a fusion of extrusion-based printing, so high precision glue gun, and metal injection molding, which has been in the industry since, I believe, the 50s. So that process has been around for a while. We're just leveraging the back end, hijacking the front end. So instead of injecting a binder with metal powder in it, we're printing with a high precision glue gun and then washing and sintering it the same way the MIM industry would do. And so how does MIM work? How does the atom process work? So as you can see from this slide, after you print, you get what's called a green part. That green part has both the wax and the plastic or the polymer binder material that's holding your metal powder. Then you have what's called a green part or a brown part after it comes out the wash. So the wash removes the wax binder. And then when you sinter it, it finally vaporizes the rest of the binder material and sinters your metal powder. And this is kind of what it looks like in a rudimentary sense. Is your metal is in the gray, your wax is kind of that orange color, and your polymer binder is that blue color. This is how our printers will print out your part, where the metal powder is suspended in this binder material. From there, when it becomes the brown part, the wax is completely removed and the metal powder is now suspended by the polymer. After sintering, the polymer is vaporized and the metal powder begins to, due to molecular forces, start attaching each other and binding together to form a fully dense part. So at Post-Sinter, that part shrinks down roughly 17%. So our software accounts for that shrinkage depending on what material you choose, whether it be 17.4, which is what we have right now, to H13 that's coming out very soon, the A2, the D2, Titanium 6.4, Inco 625, all those that are coming online will be able to be printed by the same printer, will be able to wash in the same wash, and sinter in the same oven. So like I said, part scaling is taken into account by our Eiger software, sorry. You design your part in CAD, you export it at nominal, upload it to our Eiger software, and it will scale it the 20% that it predicts to account for the shrinkage. After it's printed and sintered, the finished part will shrink back to size as designed. So when you upload that part into our Eiger software, you can choose the part orientation, select what metal you'd like to use, and that's what's so nice about our printer versus the powder bed systems that are out there. Our metal printer, you're able to swap out materials. Because it's on a spool, there's no free-flowing powder. You don't need to house your printer in the bomb-safe room. You don't need to house your printer in an environment where it's not combustible, right? You don't have to have the bunny suit, the respirator mask, so that you don't breathe in any free-flowing metal powder into your lungs or get it onto your skin and it creeps into your pores. Because it's bound, our material is bounded in that wax and that polymer, there is no free-flowing powder. So when you need to switch out materials, you can do so freely without risking cross-contamination. You don't have to have a whole separate $1 million printer just so you can use two different materials. Our one printer, one wash, one sinter oven can do all our materials. Eiger will be able to quickly, in real time, generate your cost of your materials being used, as well as the time it's going to take to print and wash your part. From here, you send your part to the printer and you just walk away. Here on the left is giving you all that information. That's where you're getting your print time. That's where you're getting your material cost, the weight of the part, how much material you're consuming with this print. And this accounts for support materials. You can see here there's overhangs, accounts for all the material being used. It will also give you warnings, and it will tell you information about your part. So here it's telling you that it's accounting for shrinkage. So your part is scaled up. You see in the part details, you have printed dimensions versus your final part dimensions. So this is what it looks like when it prints. This is a video. What you're seeing here is that part that you saw on the previous screen being printed. You can see the supports, and you can kind of see that white line or white material that's in between the part and its supports, right? Like I said, that has an overhang. So that white material is actually a ceramic release layer. So what's cool about that, you throw that part into the sinter oven, after it sinters, unlike the powder-based systems, you don't need a EDM wire cutter to take your part off the build plate. You don't need to post-machine your part off its supports. After it sinters, that ceramic powder never gets fully sintered because we don't get to the sintering temperature of ceramic. We only reach the sintering temperature of 17.4 stainless steel. So what happens in this case is the powder remains, you can pick your part right off its support. So this is a video of how we're removing a green part. So this is after it just printed with the wax and polymer binder still in there from its print bed. All right, so they're opening up the, like I said, it doesn't need to, you don't have to wear a respirator mask or a bunny suit or have a bomb safe room or even wire EDM this part off. All you do is take the print sheet out of the printer and you just peel your part off the print sheet. And now it's ready to go into the wash. So when you place it into the wash, the workflow is measure your part, the weight of your part, record that weight, and it will kick off a timer in Eiger. And what's great about Eiger, it's integrated with your account, and it will send you an email when your print is complete. It will send you an email when it's ready to wash, when your part is in the wash, and when it's done washing. Let's see. After you allow it to drip dry, because there is a solvent in the wash, it's called Opteon SF79. It's an off-the-shelf chemical industrial grade degreaser that we use to remove the wax from your green state part, producing now a brown state part. So this person is placing the part into the wash. It kind of looks like a French fryer. So then this is just showing you it drying. All they're doing is taking out that rack and placing it on the other side of this washer so that they can allow the part to just air dry. From there, the workflow, remember you weighed the part before you placed it in there. You now reweigh your part. As long as it dropped 4.2% by mass, your part is ready to go into the sinter oven. This is a video of how they're loading a part into the sintering oven. So that part is now a brown state part. It's done washing. You place it on the setter plate, and you slide that setter plate into the sinter oven. So right now everything's at ambient. You seal off the sintering furnace, and you kick it off. So he's sealing it off now. From there, once again, Eiger is accounting for the sinter run. So in that video, you saw that he placed one part in the sintering oven. You can place multiple parts into the sintering oven. As long as you fill that setter plate, that's where your economies of scale start kicking in, right? You print, you load up your wash with as many parts as you need to wash. All of them are going to be timered and accounted for in Eiger. You'll get an email when it's done washing. Pull your part out, place it all in the sintering oven, kick it off. 24 hours later, you have your finished part. And so this is what it looks like unloading the part from the sintering oven. It's hot, so he's wearing gloves. And now you'll see he has his fully sintered part. So what it's sitting on is what's called a raft. That raft is accounting for, and you see how he pulls off the part right off the ceramic release layer. That raft is accounting for kind of the drag forces against the setter plate so that it can ensure uniform shrinkage. So this is what the finished part looks like. This finished part is 17.4 stainless steel. Anything you can do to 17.4 stainless steel, you can do to this 3D printed part. Remember, we only hijacked the front end of metal injection molding. So instead of using an extruder and injecting the metal powder bounded in material, in a binder material, or using a high precision hot glue gun to print the material or print your part. After that, everything's the same. So you can heat treat the 17.4 stainless steel, you can weld to it, you can machine it, you can polish it, you can do whatever you need to do to hit any kind of critical dimensions. You can tap it so you can get the threads you need. Anything you can do with 17.4 stainless steel, you can do with this finished part. So how do I adapt existing designs for 3D printing? Right, features to consider adapting for 3D printing or any kind of threaded features. Cantilever features that you currently have. So this is saying, hey, I have a part today and I want to use it for 3D printing. Can I just print it? And these are the questions you're going to have to go through. Do they have threaded features? Yes. Do you want to print those threads, or do you want to leverage off-the-shelf threaded inserts or nuts or bolts? Cantilever overhangs. You want to minimize support material being used, so you minimize your cost of materials, minimize your print time. Right? Surface finish requirements. Like I was saying with the 17.4 stainless steel part that we just printed, if you have those critical surfaces, add on some machining stock so you can go back and machine that surface to be within tolerance. So treat it as a casted part. Interlayer shear strength. So understanding how to orient your part so that your part is strong enough to resist the forces during its function. Right? So threaded features. See, we have a heat set insert on the far left. As we move across from right to left, the pull-out strength increases. So your heat set insert on the far left is going to be your strongest in pull-out strength. Then comes a square nut, a hex nut, a helical insert, or if you tapped or printed your threads. So we're purely looking at composites here. You can also use any of these solutions for your metal. You can also print your threads, but I always recommend tapping those threads or using helicoils. So this is kind of the best practice here. And someone had the question of, oh, do you guys have tutorials or walkthroughs online? We have a lot of information on how do you design for heat set inserts, off-the-shelf heat set inserts from McMaster-Carr. How do I CAD in and make sure that I have a part that's the whole size is created so that I can use off-the-shelf inserts. And we have all that material online. And so heat set inserts is one of our go-tos for our composite parts when you're looking at threaded features. Also, square nuts or hex nuts. This is an example of a hex nut that's shouldered up on one side of this pipe bending tool. So it's very easy also to embed parts. So right now, mid-print, this person has taken the print bed off the printer, press fit or placed into the cavities the hex nuts, and now the printer is printing right over them. So you can set into Eiger, into the slicing software, exactly when you want it to pause, email you that it's ready for your captive nuts. You walk over there and you drop in your nuts. You can drop in RFIDs, you can drop in magnets, wherever your imagination takes you. Helical inserts are also great to use. Like I said, I like to recommend using these whenever you have either damaged threads that you have initially printed, or now you just printed for the application of using helical inserts. So threaded features, avoid printed threads whenever it's possible, right? You can really only achieve the pull-out strength of the nylon material, if you use printed threads. And it's best if you are going to print your threads or to print holes in the axial direction in the z-axis. Printed threads, we can get down to a M3 or an 8 thread, and only good for a single installation. So if you are removing a heat set thread, you're placing it back on there, you're really going to shorten the life of that part. This is just a high level graph once it's distributed out, and you guys can take a look at this information and understand where do I, depending on my requirement, am I looking at torque out strength? Is it a very small profile? Ease of installation? What are my requirements for that thread? If I don't really need pull-out strength, I don't need to use a heat set insert. Maybe I can just get away with using a hex nut or a square nut. So avoid orienting your part to where you're going to use a lot of support material. For example, this part is a door handle. Oriented in this orientation, you're going to have support material to support that entire length of the handle. So whenever you have these overhangs and bridges, try to design them with chamfers 45 degrees so that they are self-supporting overhangs. Anything less than 45 degrees from the horizontal will require supports. Or sorry, more. So how do you get away from these support materials, especially if you're printing horizontal holes? It's creating a teardrop profile or a diamond-shaped hole. For example, this part that our customer used was actually drawing a vacuum, and that black part is what we printed. It's drawing a vacuum throughout the entire part through these channels, diamond-shaped channels that we were able to design in and print with no support needed. Also, if you have requirements for surface finish, there's surface finish versus time, right? The higher resolution, printing at 50 microns, so very thin layers, 2 thou layers, or 2 thou slices, that's going to take a very long time to print. Well, not a very long time, but a longer time that it would take compared to if you printed at 8 thou or 200 microns. So depending on what your requirements are, whether it be print time or surface finish, you have to kind of give or take here. So selecting that layer height, you can see far left is our 50 microns or 2 thou layer height versus 200 microns or 8 thou layer height on the far right. So choosing the proper layer height, right? Thicker prints faster. Thinner gives a better surface finish. We have it defaulted at about 100 micron, which is the kind of sweet spot in between. And sometimes you need more strength in the Z-axis. So if you're familiar with 3D printing, you'll know that inner layer strength, so printing in the Z, when you go up a part, that strength and tension is a lot weaker than your XY when you're printing parallel to the print bed. So how we counter that is using bolts for Z-axis strength, right? For example, this part that was printed in the center picture in that orientation, that column that's rising up is going to be a lot weaker if you pull the in tension. So what do? We add a little pre-compression with this bolt and a nut. So prints in the Z, obviously, are going to be the weakest. Designing through bolts in those regions where you need the Z strength. If you need the Z strength, those regions, as well as in the XY, and you can't find the right orientation, this is a solution. Add fiber to reinforce under the bolt and the nut to distribute that compression force across, that bearing force, essentially, across the face. This is what we did with the tube bending die. So quick design example here, where we go over how you can iterate quickly with 3D printing, right? We kind of talked about those jaws, those gripper jaws, all right? And this is another type of jaw that was seeing a lot of abrasion, right? It was a 3-jaw gripper that wore really quickly because of the threads, the ID threads on the part it was picking up. So how do we extend the jaw life while retaining fast iterations? We could go to a metal solution, but metal maybe take longer. So how do we keep composites while preventing our composite material from wearing away, therefore extending the jaw life? So instead of printing with just the nylon, we created cavities to press fit dowel pins, just like the gripper jaws we looked at earlier, where we designed in cavities for key inserts as wear surfaces. We're doing the same thing here. We're designing cavities to press fit steel dowel pins that you can get off the shelf, so that now those dowel pins are the wear surfaces, extending the jaw life. So what if the jaw pressure causes the pins to damage the internal threads, right? What if that pressure now, you save the jaw's life, but you're damaging the ID threads that are critical? 3D printing offers us a high geometric control and fast iteration cycles. So what that means is you can take your 3 jaws with the 2 dowel pins, you can iterate to having multiple jaws with 12 dowel pins on there to distribute that kind of compression force on the ID threads. You print off a set of these. That's not enough. You iterate to the next design in CAD. 15 minutes later, you have a new design. So it's very easy to design in CAD and see your solution in your hands very quickly. So rapid design iteration on your tooling, go from a baseline to understanding how much does a reduction in contact surface save the ID threads of my actual production part. So this goes back to what we were discussing earlier, where in the time it would take you to get Rev A done in a traditional manufacturing, you can go through Rev B, Rev C, Rev D, even Rev E before, in the same amount of time it took you to get Rev A with 3D printing. So a little bit about Markforged. We're trusted by industry leaders. This is a slide on all the companies that we've worked with and the solutions that we provide for them. A little bit about Markforged. We were founded out of MIT back in 2013. We're headquartered up in Boston, Massachusetts, with now near 200 plus employees and growing every day. We shipped our first printer back in 2014, and year-over-year growth, we're looking at 300%. As of, I think, last month, November, we had our 200th metal unit in the field. Now, Markforged is a complete solution. So what that means is we have software engineers that handle the software, that produce the slicing software, that push new updates, fix bugs every day. We handle the hardware. We have 2 contract manufacturers up in Boston that produce our printers, manufactures our printers. So by controlling the software, the hardware, as well as producing our own material, all that engineering grade material, the onyx with the chopped carbon fiber, the continuous carbon fiber, Kevlar, fiberglass, all of that material is produced in-house. So by controlling all 3 of those variables, we control all possibilities of failure and ensure all possibilities of quality, or ensure all aspects of quality. So Markforged enables customers to produce stronger, functional parts faster and at a lower cost that serve the needs of a wide range of applications across the entire manufacturing lifecycle. Thank you guys for your time. And are there any questions?
Thank you. Great job. That was so informative. There was one more question. Jim said he already owns a Markforged printer and he wants to know how he can get the biggest return for his investment quickly.
Okay, yeah, so identifying a lot of those applications on your shop floor, if you do work in a shop floor environment, those are where you're going to kind of find the quick wins. What I like to ask our customers to do is kind of sit back and think about what are the major cost drivers and pain points in your business today. What is causing you the most money, the most headaches? What's like a pain in the butt because you have to source it out to this one vendor, or they're always taking 4 to 6 weeks and it keeps getting pushed back. There's delays in production or delays in the delivery of a part. What is holding up your business? What's causing you to lose money? What's causing you to lose sleep? Anything like that are usually good candidates for, okay, this might be a good candidate for 3D printing. From there, you can kind of figure out what's the greatest return on getting that part printed. How many parts are you looking to print? So there's a couple of variables you balance there to quickly get a return. But usually it's your high lead time parts, your high cost parts, and the ones that are one-off or you scrap after you use for one time.
Yeah, and if you guys have, if you guys just kind of want to talk through your processes with, you know, any of the experts at Markforged or at Saratech, we would be happy to set up a call if you just want to talk through your processes and the way that things work and see if we can help you be a little more efficient. We would be happy to do that. We do have another question from Dan L. It says, how long before you can use aluminum in the Metal X?
So aluminum in the Metal X is in R&D right now. There's still the complexity with aluminum is sintering. So the easy step, well, I say easy step, but the easier step is really printing and washing that part. It's how do we make sure that as we're sintering the part, we're sintering it at a pressure and profile that's going to ensure the part quality, right? That's not going to have internal crackings and internal stress that's occurring that we need to relieve and throughout the process. So that's right now being figured out by our R&D team. The market that we looked at to get into with the Metal X has been heavily into manufacturing. As you see the roadmap for our materials, H13, A2, D2, so injection molds, injection blow molds, die stamping, sheet metal forming, things like that is kind of the industry we're going into. And we're seeing that that's where the most need is and that's where the market is. That's not without saying that aluminum is not a huge market. We know it is. It's the most machine material. And so we are still pursuing that heavily. But it's kind of still in the R&D phase, whereas the other ones are in beta.
Okay, I hope that answered your question. We do have another one from David. He wants to know, what is the thinnest wall a titanium part can successfully print, like the thickness of it?
The thinnest wall are composite printer or?
I'm not sure. David, do you want to just type in another question there and let us know if you're asking about a composite printer?
So I can kind of address both
yeah, maybe that's better.
The composite, we can print the thinnest wall as 0.8 millimeters, which is, I can't do that math in my head, divide by 25, or it's 0.8 millimeters is what we recommend. We can go as thin as 0.4, which is our nozzle size, but that's not recommended. It's very unstable because it is so thin. 2 walls is usually the thinnest we like to go, which is at 0.8 millimeters, and our default is always 1.6, so 4 walls. Our metal printer follows along the same guidelines. Our walls are normally printed at 4 layers, so 1.6 is the min wall thickness for a metal. But that metal that's printed, so it shrinks down, whatever that 17% shrinkage is.
Mm-hmm. That is tiny. It's crazy to think it can go that thin.
Yeah.
Okay, I think that's all the questions we have right now. If you guys think of any other questions, there is a quick little survey that pops up as soon as we end the webinar here. And if you could just let us know how we did today, and also please, more importantly, let us know if you would like to hear more from the Markforged team, or if there's any other topics that you're really interested to hear more about, please let us know. We are ramping up the 2019 CES sessions right now, and we take your suggestions very seriously. So please make sure you put those into the survey. And then do you have a couple more slides for me?
Yes.
Okay, awesome. Like I said, we would love your input. So just make sure that you join us for the 2019 series. We'll be posting some of those on our website here soon. And if you're ready to take it to the next level, if you just own, maybe NX right now or any kind of CAD software, and you're ready to start talking to Markforged about, maybe which printer would be best for your business, please let us know. You can email us. Probably the easiest way to email us would be marketing@saratech.com, and then we will make sure that that gets off to the right people. And then, like I said, we'll be, we recorded this today. We'll be posting it to our YouTube channel. We'll be sending it out to each of you. And in the future, if you're not able to make it to any of our sessions, you can go ahead and just register for them, and we'll be sure to send the link out to you. And then today we will also, I guess, LaShawn has some extra little goodies for you. So we'll be attaching some design guides to the email as well that should be going out to you today or tomorrow. And if you could just, I think that's it. One more slide. Yep. And if you could just stick around and fill out that survey, just a couple of questions, we really appreciate it. No, we went a little longer today, but I think it was worth it. And I hope you all have a wonderful rest of your week. And thanks again to our presenter.
Thank you, guys. I appreciate your time. Have a
Yep.
wonderful
Thank you.